Hey everybody, my name is Taylor Sparks, and today we're going to talk about lattices and symmetry in preparation to understand crystal structures. Most material science, approaches, they dive right into the structures like BCC, FCC, HCP. But before we do that, in this series of lectures, I just want to provide a video or two where we talk about the underlying symmetry that will help you understand crystallography in general before we dive into these specific structures. So that said, there's some great resources online. My very favorite to recommend you, it's not online, but this book called Crystals and Crystal Structures by Robert Tilley. It's fantastic. It's easy to read. It strikes a nice balance between being approachable. It's not necessarily too introductory because it gets into some of the details, but it doesn't lose you in the complex math and things like that. He does a really good job, so highly recommend it. But there's other resources. Mittermeier's book, Chapter 4, has some great stuff. So those are good things to look into. And of course, these notes that I'm going to describe today. So why bother with crystallography and lattices? And, underlying all of the different crystal structures is this idea of symmetry. Symmetry exists in nature, and it's a way of describing structures in a much simpler way. So for example, there exists lots of crystal structures. Let's take a look at one, right? Let's look at Murataite crystal structure. So Murataite is a sort of a complex ceramic structure. And when you dive into it, this sucker is gnarly. Here's just a glimpse of it. It's got, hundreds of atoms in the unit cell or something like that. And you can see that it's really complex. And you're left wondering, are all of these oxygen atoms, for example, do they have the same local environment? Or is it different? Well, what about the polyhedra, these groups of, this is what we call an octahedra. It's like two pyramids set on top of each other, bottom to bottom. Are those the same crystallographically? Do they have the same sort of environments, or are they different? It's actually really useful to use symmetry to describe things so that we know what in this overall picture of the unit cell has the same local environment. Because usually that's what's going to dictate the properties and help us understand the structure. It's also a much simpler way to describe it. Here we have hundreds of atoms, but if you think about it in terms of symmetry, there's a few unique positions, and then when you apply the different symmetry operators, which we're going to learn about in these videos, it produces all the rest of those atoms. So instead of having to keep track of every single one of those, saying X, Y, Z coordinates, you find an atom here, and you find an atom here. Instead, you say, here's the basis of a few atoms, and if we apply symmetry, it gives us all the rest. Okay, so what exactly are these symmetry elements? Well, there's a few, right? We're going to start with the most basic, okay? The most basic symmetry element is going to be translation, right? In fact, translation is what makes up a lattice. A lattice is nothing more than a continuous series of repeating units, right? So for example, here we have an example of a lattice in one dimensions, right? These are showing you little spheres, which could represent atoms, but a lattice doesn't have to be atoms. It could be a lattice of just positions. And you see that in this, there is a translation. As we go from one to the next, we can translate some distance t. And if we keep on translating that the exact same distance, we end up with this chain of positions, right? Now, those positions can be occupied by atoms. And when you put atoms on top of a lattice, you end up with a crystal, right? So a crystal is a region of a lattice occupied by atoms. And we know that in materials, it's not infinite. You don't have infinite many crystals. A lattice extends infinitely, but a crystal has finite bounds. That might be a lot of atoms. It could be millions or billions, right? It could be many, many, many atoms, but it is technically finite. But the underlying lattice could go on forever. It's just that you run out of atoms to occupy it, or you bump into something, you run into eventually what we call grain boundaries, for example. But here's an example of a one-dimensional lattice. It is periodic, right? It repeats at the exact same distance over and over in one dimension. And we need one vector, a translation vector, to describe that. Now, this could exist in two dimensions, right? A lattice can also be two dimensions. Here we go. Here's a two-dimensional lattice. This time, you have two vectors that represent the ways that you can translate it as it continues to fill all space, right? You've got one vector that can go like that, and maybe one that can go like that. So you have these vectors. Now, here in this exact example, it's a square lattice. So those vectors are the same magnitude, just different directions. One goes in one direction, one goes in an orthogonal direction. But they don't have to be the same magnitude. You could have a hexagonal lattice, right? Something like this. This would be another example of a crystal with a rectangular underlying lattice, right? And this would extend as we go. In this case, you would have one vector of translation here that's a little bit shorter than this one, which is a little bit longer. So this would be T2. That would be T1, for example, right? And obviously we could extend this now to 3 dimensions, where most of material science happens is in 3 dimensions, although 2-dimensional materials are a very big deal right now. But most of the time in material science, we're talking about 3 dimensions. So of course, now we need our overall family of translations that can occur is now a combination of translations in the 3 different dimensions. And the definition of a lattice means that as long as you take an integer number of steps along any one of these, positive or negative, right? You can start with this guy down here, for example. You can take a positive step in that direction, positive. You can go back negative that direction. You can go negative or positive, however you're defining your axes. And as long as you take integer number of steps, you'll end up on another lattice point of your crystal, right? So that is the fundamental aspect of symmetry, is translation. Okay, ready for our next one? Our next symmetry element goes beyond that to include rotation, right? So now we're not just going to rotate to end up with an identical lattice or an identical crystal. Now we're going to rotate the entire crystal, and by some angle, right? If you think of rotation, if I take this pen, for example, and I'm rotating it about, in this case, the axis of the pen, and I'm rotating it some degree as I go around it. Maybe it's a full rotation, which would give you just the identity, right? Wherever you started at, you're going to rotate all the way around. You're going to end there again. Okay, that's an identical crystal. It's not a very interesting one. It's just the identity rotation, right? But maybe you rotate it half a way around, like 180 degrees, and you end up with another atom. Or maybe you rotate it 90 degrees, 90, 90, and then 90 again, and that gives you 360 degrees. And at each one of those rotations, you end up with an crystallographically identical lattice, right? That's a symmetry operation. So we call these n-fold axes, right? Where n is the how many rotations it takes to get back to where it started. Like a 4-fold rotation takes 4, right? You go 90 degrees, that's rotation 1. A second 90 degrees brings you to 180. A third rotation brings you to 270. And a fourth rotation brings back you to 360, right? So it's an n-fold rotation, right? So what would an n-fold rotation look like? Well, let's go back to our square lattice. It has a good example of this. So if we take our square lattice, right? Let's just do it in 2 dimensions so it's easier to visualize. If I take this thing, I can rotate this lattice, right? If I rotate it, like if we're going to rotate around this point in the center with the little tiny black dot, we're going to rotate it 90 degrees. That's our first, right? Rotation, right? Alpha is equal to 90, right? If we rotate that entire lattice, that atom ends up on another lattice plot. In fact, it's exactly identical to where it was before. I can rotate it a second time and it brings it here. I can rotate it a third time. I can rotate it a fourth time. So this lattice has 4-fold rotational symmetry, right? It also has 2-fold rotational, right? Because I could have also done this. I could have said, just rotate it 180 degrees, right? But it would be a higher symmetry to say that it has 4-fold, right? We're skipping something if we just do 2-fold, okay? Similarly, we can see that in graphite, right? A single sheet of graphite or graphene, we can look at this and we can identify the symmetry present. And it kind of depends on where we start with. For example, if we start right here in the center of this, we can see that this has 6-fold symmetry, right? If we rotate this atom 60 degrees, it goes there, another 60 degrees, another 60, right? 60 degrees at a time times 6 gives you 360 degrees. So that has 6-fold rotational symmetry. By the way, the term that we use when we draw these things to indicate that symmetry, we draw a little tiny, I'm going to zoom in, we draw a little tiny hexagon, right? So I'm going to draw it like this, okay? But there's also a 3-fold symmetry in this lattice. Can you see it? There's a 3-fold. Let me draw it in a different color. If we choose this one, I'm going to draw a triangle. That's how we denote 3-fold symmetry. This guy could rotate to here. This one could rotate to here. This one could rotate to here. So the same underlying crystal structure, which is occupying a lattice, right, can have different symmetry elements present in it. Here we can see an example. There's both 6-fold rotation and 3-fold. By the way, the rotation has to act on not just the atoms that are nearest neighbors, it has to act on everything. So let's go back to our 6-fold. Again, it's acting clearly on these neighbors immediately around it, but it also acts on everything. Like this guy also goes 60 degrees. 60 degrees, 60 degrees. It acts on everything. Similarly with the 3-fold rotation, we have the exact same scenario happening, okay? So there's an example of rotational symmetry in graphite where we have both 6-fold and 3-fold, right? You've got 6-fold and you have 3-fold. Just like in the square lattice, we had 4-fold and 2-fold, okay? All right. Now, of course, if you had like a perfect arrangement of hexagonal atoms, that would also work, right? If you have taken a material science course and you've seen like hexagonal close packing, then it looks something like this. If you haven't, we're going to see it in just a few slides. But it looks something like this, right? This one, at any one of these atom positions, we can draw our hexagonal rotational axis. And again, we go to 60, 60, 60, 60, 60, and back again, and it rotates. Every time that you rotate at 60 degrees, you end up with the exact same crystal that you had before. Therefore, it is symmetric, okay? Now that said, there are only certain types of rotations that are consistent with lattice periodicity. We said that a lattice, right? If we draw the underlying lattice, right? Whatever the shape of this lattice is, the angles between it, right? Whatever this lattice is, where you have things existing, you have certain constraints that the rotation has to end up with a lattice underneath it, right? And because of that, there are certain constraints where only certain angles are allowed. Let's show you an example, right? The derivation of this can be seen, but I'll just do a simple derivation here. Let's start by drawing a lattice, right? So we're going to put something like this, for example. Let's assume that we have atoms at the corners of this shape, okay? Now, if this distance is t, and that distance is t, that distance is t, but this one up here is some integer number multiplied by t, then we can rotate our, like this, by alpha. This would also be alpha, our ability to rotate that way, right? You can show mathematically that p must be an integer, right? We'll say that this guy, p must be an integer. Okay, and if it must be an integer, then we're left with this series of equations. We can write that t plus 2t times sine of the angle minus 1/2 is equal to pt. A little bit of geometry happening behind the scenes for this. These equations all hold. Therefore, we find that cosine alpha must be equal to 1/2 of 1 minus p. And if p is an integer, let's just try putting a few integer values in and see what the angle, the allowable angles are. For example, if we put in the value of 3 for p, then it's 1/2 times 1 minus 3. So that's -2 times 1/2, so that is -1. Okay, so this whole thing equals -1. So what value of alpha corresponds to cosine of alpha being equal to -1? If it helps, we can draw cosine of alpha real quick, just to have it in front of us. We know that cosine alpha, as you go from 0 degrees all the way out to 2 pi, or 360 degrees, if you want to think about it in terms of degrees instead of radians, we know that cosine alpha does this thing, right? Okay, so when does it equal -1? It equals it at 180 degrees, or pi, right? So in other words, when you rotate 180 degrees, that is an allowable rotation. And you rotate it 1 time and 2 times, you're back where you started. So that is a 180 degrees rotation, and it is a 2-fold rotation, right? Okay, well, we could plug in 2 as the integer value 2, and we'd find that that is cosine, the cosine of alpha equals -1/2, and that occurs at 120 degrees, right? So 120, 120, 120, that's a 3-fold rotation. If we plug in 1, that occurs at 0, which is at 90 degrees, right? At 90 degrees, that is now a 4-fold rotation. If we do this at 0, if p is a 0, that happens at 1/2. That is a 60 degrees rotation. That is a 6-fold rotation. In other words, 2, 3, 4, and 6 are allowed. A 5-fold rotation is not allowed in a periodic lattice. Now, some of you might have already jumped ahead and learned about quasi-crystals, which are a different way of thinking about this. They were discovered in the 80s, 1982, by Daniel Sheckman, and we're going to cover those in a different video. But for now, in the world of like pre-1982, they could not conceive a scenario whereby you had a periodic continuing lattice with anything except for a certain number of rotations, and 2, 3, 4, and 6-fold were allowed. That is our rotational symmetry. Okay. Let's switch gears and talk about our next symmetry element, which is reflection. Reflection is just like when you look in a mirror, right? When you look in a mirror, you see the thing on the other side at the same distance. So we can have mirrors that represent atoms, right? So let's put our atoms. Let's put an atom here and an atom here. Let's put an atom here and an atom here. In this scenario, we can identify a mirror plane. I'm going to draw out that vertical line there, right? And now the distance between these atoms is preserved across that mirror plane, right? sometimes in geometry we do these little hash mark symbols to show that they're equivalent distances, right? The distance from A, right? We get the atom A prime when we reflect it across some plane, right? The atom at position B gets reflected to some position B prime, for example, like that. And there's lots of molecules that exhibit symmetry, right? So for example, let's take this compound here, cis H2Cl2C2. I am not great at my organic names, so whatever the name of that molecule is, right? Let's draw it out. We've got carbon double bonded to carbon, and cis means that the non-hydrogen group is on the same side, right? So we've got our hydrogen over here, we've got chlorine down here, we've got hydrogen up here, and we've got chlorine down there. You can see that there exists a vertical line where now you have symmetry. All the atoms that exist on one side have their reflection, a reflection symmetry onto the other side, okay? So that is our next one, reflection. By the way, it doesn't have to be a vertical plane, and it doesn't have to be just one. You can have multiple different reflections present. These are called mirror symmetries, and you can have multiples. In fact, sometimes by having two, you create a third by automatically. We'll show you that later, okay? All right, the next symmetry element that I want to show you is inversion. Inversion says there exists a point in the lattice, not a plane, but a point, where if you take all the atoms and you pass them through that point to the other side, you end up with an atom in the same position. So it's not the same as a reflection. A reflection happens across a plane. Inversion happens through a point. So let's draw an example of this. Let's say that I've got an atom A and B, right? So, and then I have an inversion point right here, right? We'll call that an inversion point I. So if I take atom A and I take atom B and I invert them through it, that gives me an atom A prime over here and B prime over here, right? These distances are once again preserved as we invert them through that inversion center, right? You can see that's not the same thing as a mirror reflection. If we had like a vertical line or even like a horizontal line, it would not be the exact same thing. This gives us different symmetry, right? And there's examples of this in molecules too. In fact, if we take that exact same molecule we showed you before, but we do the trans version of this molecule, now the chlorines are opposite sides. Now this has inversion symmetry, right? We take our carbon bonded to carbon, that's a double bond. In this case, you've got hydrogen up here and chlorine down there. But because it's now a trans molecule, the non-hydrogen group is now on the opposite side. Check it out. There now exists an inversion center right in the middle of that double bond, where if you invert all the atoms from one side to the other, right, they invert and they get to the same position where they were before, but on the other side, okay? So it has inversion symmetry, which is not the same as reflection. Something else to think about is there is this idea of enantiomorphism, which is when compounds have a handedness or a chirality, just like your right hand and your left hand have a handedness to them. So these cannot be made to coincide by either translation or rotation, only by reflection or inversion. So here's a good example. This molecule here, whatever its name is, right? You can see that it has a an acetate group. It has a hydrogen, an OH, and a methane group on the sides, or a methyl group on the sides. So it could be arranged like this, or it could be that mirror reflection on the other side. By the way, if you're new to organic chemistry, these symbols, the solid line means a bond, and those bonds are happening in the plane of the screen. But the bonds here with the dashed lines, that means that it's going into the screen. And the solid sort of like getting wider line means it's coming out towards you. It's trying to show kind of perspective, like one's going back, the hydrogen and the OH in both groups is coming towards you. Maybe you've seen this before, but that's what it's showing there. And there's lots of examples of enantiomers that you might be like, oh, well, okay, yeah, technically they're different, but who cares? Who cares is because they are very different. I just pulled it up on ChatGPT just to ask it. I was like, give me some examples of famous enantiomers that have way different properties. And this is the one I was hoping to find. I'd heard of it. So thalidomide, this is a drug that was used in the 50s and early 60s, and they used it to treat morning sickness in pregnant women. But there's two enantiomers that exist, and one has a sedative effect and was intended as a therapeutic, but the other actually caused severe birth defects, phocomelia, right? So you can imagine that if you didn't synthesize the right enantiomer of this therapeutic, you might actually be causing real harm or birth defects. So it makes sense because this happens in compounds primarily with carbon, which have this fourfold bonding, right? These tetrahedral bonding, there tend to be chiral ones. And our body is made of carbon. So we tend to have a lot of chiral components to our body. And if you bring in a drug or some sort of molecule, it might only bind or interact with bonds of a certain chirality or compounds of a certain chirality. Therefore, this becomes an important symmetry to consider. Okay, so those are our basic symmetry elements. Of course, there are some that exist out of combinations of elements. We said before, for example, we showed you with graphite or graphene that you've got both, where is it? You've got both threefold and sixfold, so you can have multiples. Well, sometimes when you have multiple symmetry elements, it creates another one, right? So let's take a look at this one. Roto-inversion is an example of a combination of elements. We're going to rotate, and then we're going to invert, right? So the good example of this can be seen by examining both the top-down view as well as the side view. So let's first look at the side view. Let's imagine a scenario. Let's draw some axes where we have, we're looking along the side. These dashed lines represent like constant height, top and bottom, right? So I'm going to draw with the notation that says like the filled in atom like that represents that it's on the top, and the open atom represents it at the bottom. Maybe it's the exact same, atom, but that's just going to show which ones are on the top versus the bottom, such that now when we look down on it, imagine that we're looking down on a series of molecules. Let's imagine what would happen if we did a fourfold roto-inversion, right? We draw this with a 4 with a little bar on top. That means that it's a fourfold rotation followed by an inversion. So let's start with an atom. We're going to draw it here as a solid point. That means that it's on the top layer, right? Okay. Now, if we do a fourfold rotation, that's going to bring it up to here. That's going to rotate it to there. 90 degrees brings it to the top of the circle. But now we're going to invert through the center, where the center is this guy right here. So it's going to invert it through the other side. So that's going to bring and take that atom, and it's going to put it on the bottom right there. That is our first rotation. It put it there. Okay. But because it's a fourfold roto-inversion, we're going to do this 4 times to get back to where we started from. Okay. So the second one, right, this is number 1. Right? The second one is going to bring us here, but then we have to invert. So because it was on the bottom as it was rotating, now it's going to invert through it, and it's going to come back to the top, which is going to put an atom right here. So that's our second of our 4 roto-inversions. So now we're going to do it again. We're going to rotate this one again 90 degrees the same direction. That brings it here. That's number 3 rotation. And then we have to invert it. It's at the top currently, right? When we rotate, it's at the top. So when we invert it, it's going to go back to the bottom. It's going to put an atom right here. Now we're going to do it one more time. Our final of our 4 rotations is going to bring it to here. That's our number 4. And when we invert it, it's going to come back. And because it was at the bottom before, it's going to rotate back to the top, which is where we started from. In other words, it gives us the exact same lattice where we started, right? That's what it's supposed to do. That is a roto-inversion, a fourfold example one, right? And there's lots, it doesn't just happen with fourfold. You can do this with other arbitrary ones, like let's do sixfold, for example. Okay, now let's take a look at what sixfold roto-inversion would do. So again, let's draw our top view of this thing. It's going to help to draw our 60-degree rotation lines. So I'm going to draw those in green just to make it easier to see. Let's imagine we start with this plane. Our first rotation, our first 60 degrees is going to look like that, right? That will give us 60 degrees. We do it again, that's going to give us 60 degrees, 180, right? So we can see that there's 6 rotations here. Now it's again, just like before, we're going to apply our atoms, right? So we start with an atom above right here. The very first rotation, right, of the 6 that we're going to do, the first one's going to rotate to here. That's our number 1, right? Because it's starting out above and we're going to follow it by an inversion, it's going to go from the top down to the bottom. So that's going to put an atom right here, right, on the bottom. Let's show that in dark. Okay, now we follow this with another rotation. This is number 2. That's our second rotation. Because it was on the bottom before, it's going to invert to come to the top. Okay. Number 3, our third rotation, puts it here. Because on the top, it's going to invert to the bottom, which is not the same place as we started. There's an atom now above and below, right? And now we go to, that was our third rotation. Our fourth one is also right here, that same rotation. But because it's starting on the bottom, it's going to invert to above, which puts an atom directly above that. And then our 5th rotation down here, right, is going to be the same, but it's going from above. And then we're going to invert down to the bottom like that. And then our 6th rotation is right there. Because on the bottom, it inverts back to the above where it started from, right? Pretty cool, right? That is an example of a 6-fold roto-inversion. And if you look close, you could imagine that this is actually equal to several other symmetry elements combined. This is equal to a 3-fold rotation and a mirror symmetry, right? So this one symmetry operator is actually composed of two other ones. Like if there was a mirror plane in the sheet of the image here, there's atoms above and below that symmetrically, and there's threefold rotation, right? Same. So this produced the same thing, right? And then if we look at threefold roto-inversion, it would look like this. Threefold roto-inversion. Again, if we start with our atom here, now this time we're doing just 3 rotations. So we're going to go, right, that's how we're going to divide this thing up. So our first rotation is going to go from here to here. And because we're on the top, when it inverts, it's going to come through to the bottom, right? So that's going to put an atom down here on the bottom. Now we're going to do it again. Our second rotation, that was number 1. The second rotation is going to bring us to here. Because it's on the bottom, it's now going to invert to the top, which puts an atom right there. The third one is going to go here. That's our third rotation. It's on the top, so it's going to bring it down to the bottom. Now we haven't gotten back to where we started from, so we're just going to keep on rotating until we get back to where we're doing 3 folds at a time. In other words, we're doing 120 degrees, but because we haven't gotten back to where we started from, we would go again. We'd go 120 degrees, which brings us here. In this case, that's number 4. And we invert, right? And that brings us and puts us an atom on the top here. We rotate it around and flip down. That puts an atom there. Do it one more time. You're down below. You invert to the top, and you're there. So it actually took 6 steps to get there, right? And yet they were all threefold rotations followed by inversion. And that would be the structure that it produces, okay? So something to point out here is that the 4-fold roto-inversion is actually a new shape, right? This is a new element. This creates the tetrahedron shape, which we're going to see all the time. So for example, every time in material science, when you see that carbon is bonded to carbon, and then you have that bond coming out towards you to a carbon and the one going into the plane, carbon, that is a 4-fold roto-inversion that creates that shape, right? Okay. There's also such thing as a roto-reflection, where now you're going to rotate, and instead of going through an inversion point, you just reflect through some plane, for example. Those are written with the tilde sign above it, so a 4-fold rotation. In this case, a 4-fold roto-reflection is equal to a roto-inversion. It gives you the same symmetry. But a 6-fold roto-reflection gives you a 3-fold roto-inversion, right? So they're slightly different. So you can get into some examples of that. But that is a combination of elements would be roto-inversion. Okay, the next type of symmetry element that arises by combining multiple different symmetry elements is the screw axis. Okay, what is a screw axis? A screw axis is when you're going to rotate first and then follow by translating along the axis of rotation. So if this is my screw, right? We're rotating around some axis, right? But then we're going to translate part the way down, right? And the nomenclature that they use is that the first number that you see, say 3, for example, tells you how many folded the rotation is. Like 3 would be 120 degrees, 120 to get back to where you started. And then the subscript, 1, 2, 3, whatever it is, tells you what fraction of the unit cell, based off of the above number, you translate at a time. So let's look at this using the 6'1", 6'2", 6'3" family of screw axes, right? So 6'1" tells you that we're taking 60 degrees at a time. And then 1 subscript means that we're going to translate 1/6 of the unit cell. So that's this guy right here. In other words, if we started with this atom as our first position, we're going to rotate 60 degrees, right? Because it's a 6-fold rotation, followed by a translation 1/6 of the way up. So this distance right there, that is t, our total translation, divided by 6. And then we would do it again. We do our second rotation, that brings us here, and we translate up again, right? There's yet another translation. And we do this again a third time, fourth, and you see that it would come back to where we started from. That is our screw axis. Well, now imagine what a 6'2" would look like. So a 6'2" means that we're still doing 60-degree rotations, but this time we're doing 2/6, or 1/3 of the way rotation, or translation along the screw axis. So this time we're going to go 60 degrees, but then we're going to go up by 1/3 of the overall unit cell, right? And then we're going to do it again. We're going to rotate another 120 degrees. So now we're going to rotate another 60 degrees and go up another 1/3, right? So now we're 2/3 the way up. That's 1/3, that's 2/3. We're going to do it one more time, another 60 degrees would come up, and now we're 3/3, or we're back to where we started, right? You do the same thing with 6/3. This time 3/6 is the translation. That's half a unit cell. So we're going to rotate 60 degrees and we're going to go up half the unit cell. We're going to do it again. We're going to go up half the unit cell, right? So that's how the screw axis nomenclature works. And there's a nice link here if you want to follow up with that in the show notes, okay? So there's several different screw axes available. There's two. If you have two order screw axes, the only screw axis is a 2-1, meaning you do half of a translation, half a unit cell translation. But if you're 3, then you can have 3-1 or 3-2. That means you're either going in 3-1, you're going 1/3 of the way translation each time, or 3-2 means you're going 2/3 at a time, okay? You can have 4-1, 4-2, 4-3, and then all those different sixfolds, okay? Another one is you can have glide planes. A glide plane is a translation by tau, right? So in the M direction, and then you reflect about that mirror plane. So you're going to translate along a mirror plane, and every so often you're going to translate, right, after each time. So for example, this hand here is going to translate some distance, tau, right? And then it's going to reflect. So a left hand becomes a right hand on the other side. And then this one is going to translate, and it's going to reflect. And in that case, you're back to where you began, right? So t is a translation distance along some glide direction. So tau could be t/2. And we see example of this in actual crystal structures. Like here's the structure for diamond. And if you look closely, you'll see glide planes here. Do you see it yet? What about if you went from this bond to that bond, passing through these ones, right? That line, that's the plane, right? If you take that and we were to apply the symmetry elements here, this guy, this atom at that position is going to translate some distance, and then it's going to reflect over to that one. This one's going to translate some distance, and it's going to reflect over to that one. Translate, reflect, translate, reflect. You see that? So that's an example of glide planes. Okay, so those are the symmetry elements that we use to create all the different symmetry that we find in material science. It's pretty awesome. Okay, so from that, we can actually come up with our different ways of classifying different materials by the symmetry, and we'll do that in our next video.